Okay. Uh, yeah, thank you all very much for coming. Um, just so you know who I am, I run a company helping businesses adopt artificial intelligence and data science. I've been a practitioner in business intelligence, data science, and I also do a surprisingly large amount of software engineering. So I come at this from a variety of angles. I help people get into programming inside the data science space. There's a few books that you can even get free on Kindle Unlimited from me. I love helping people learn in this area. So I do lots of talks like this. And Microsoft have very kindly recognized my contributions inside data platform and AI. Do connect with me on Twitter and LinkedIn. You can also email me later on, steph@nightingalehq.ai. So 60 minutes is a really short amount of time to learn a lot of kind of the fundamentals. So we're going to start off with some overview of machine learning algorithms and how and why they work, so that we can start building on that foundation into what regression broadly means, and then taking it further into predicting numeric variables or values that are on the number scale. This is not unfortunately, not the full scope of all the ins and outs of regression. It takes a lot more time to kind of cover all of that content and understanding, but the goal really is to help you build a strong, intuitive foundation for how you can apply these algorithms responsibly and effectively. There's no Greek, no big walls of formula or anything in this. This is a kind of a very non-maths, intuition, visual reasoning based approach to understanding these solutions. So let's talk about machine learning algorithms. We're going to look at the concept of fitting a model, what a supervised model is, so that you can understand how regression fits into that. And then we're going to look at two key concepts: loss functions and error. So when we talk about fitting a model or training a model, we take an algorithm, which is basically a mathematical process, to distill the data that we look at, to turn it into a rule of thumb or formula that abstracts from all of that noisy data into something simpler that we can apply to future data to be able to make predictions. So all the different algorithms in machine learning are really about trying to find the way to best describe the phenomena in your data. And quite often, or throughout all of these models, because computers are building them, are fitting them to data, computers need to know how they're doing a good job. So we have these things called loss functions, which describe how we know whether a model is any good at its purpose. And the process optimizes and tries to manage that loss function so that, for instance, the error might be as small as possible in its ability to make predictions. So a loss function, how we know it's any good, is the other key component to when we're building a machine learning model. You have the algorithm, which creates the parameters, the rules, and you have the function that it tests whether that set of rules is any good with. As you advance in machine learning, you might find these things called hyperparameters bandied around. Hyperparameters are essentially values that govern fit the algorithm and how it fits a model. A hyperparameter could be how many iterations it runs to try and improve things. It could be how it considers to know when to stop. There's lots of different hyperparameters in various models. And some of the advanced regression methods have hyperparameters that you would be able to tune to improve how the algorithm reaches an effective model based on the loss function that you specify or the default one inherent in the coded solution that you use. Throughout this slide deck, and I'll share it, it's already on LinkedIn. If you go to my profile, data science, machine learning is really, really big. And it can be really scary because there's so much vocabulary and jargon. Chris Alban has these great machine learning flashcards that have a topic and really try and summarize it for us. So I'm going to bring these out throughout our slides as I describe concepts so that you can see some of these flashcards in action, because I really would recommend them to anybody who's getting started in data science, and also somebody who's quite advanced in it anyway, because terminology can vary quite significantly based on people's academic backgrounds or areas of focus. So even the experts need to look up terms at different times. So machine learning is all about the computer taking data and distilling it to some sort of rule so that it can do something with that data. A key type of, and probably the one that most people do frequently in terms of machine learning fitting of models, is what's called supervised model fitting. And it's supervised because we have a label, which can also be called an outcome, a dependent variable. You'll see label, outcome variable, outcome, and dependent variable used kind of interchangeably. That's a known answer. So for instance, if you're trying to predict people's height, it would be really hard for you to know whether you were doing a good job if you didn't have people's height measured so that you could check against it. But in supervised models, we use the label to be able to measure how well we're doing at producing that rule, that model, to be able to make sure we optimize as effectively as possible. There will be some combination of features in a supervised model. That means features can also be called independent variables, columns, field, variables, fields, lots of names for them. But if you think about a table of data, you'll usually have lots of attributes, lots of columns about something, and then the label might be the outcome for what happened. So you'll have features, and we usually combine those in various ways. So in regression, we'll see how they combine numeric values to be able to predict the label. But other algorithms might combine them into things like if this, then that statements to be able to produce like a decision tree to how to predict a label. So they all combine the features in some way, and they all use a loss function to be able to do this fitting exercise. And they usually, because they know the label, their goal is to minimize error. So error is the difference between what actually happened and what we predict will happen. And that's what we're always trying to minimize. So in the slides, I recap some of these additional values for you, additional names. So let's start talking some real values. I've got some data, and we're keeping it all quite simple throughout this session. You can have lots of columns that you could be trying to predict Y with, but we're going to start with just one column. We're going to try and predict Y based on X. So we've got 8 data points. In reality, you might have thousands or millions of data points, but 8 fit on a page nicely. And when X is 1, in one case, it had a value of 3 in our label or outcome variable, and in another, it had a value of 4. This carries on, and it looks like what's called a linear relationship, that as the value increments in X, we see an increase in Y that is generally proportional to the increase in X. Now, a regression is really just a line of best fit. And you might remember these from high school and things like that. And we can draw a number of candidate lines of best fit. So we can do our yellow line here is Y equals 1 plus 2 times X. The 1 is our intercept. So if we didn't have any a recorded score for X of 0, we'd predict a Y of 1. And then every time X increases, we double the value. So looking at that yellow line, it really predicts our early X values, outcome in Y, but then starts over predicting the value for later numbers. We could try Y equals 2 plus 1X, and that's really good at getting half of our data points predicted, but it misses our greater values. And then we have another option, which actually underpredicts half our values and overpredicts the other half. So it sits in the middle and is really close to both. This is how machine learning works. It goes through an iterative algorithm to be able to produce a line of best fit that will start optimizing based on the loss function. So as I said earlier, the loss function is a calculation that helps us work out how effective our model is. We usually try and calculate some sort of error and try to minimize error, because the more accurate our model is at predicting the outcomes, the more effective it will be when we use it in test data, or at least that's the goal. And it's really important to understand the implications of different loss functions. You have the option to create your own, and that can be really valuable in or change the hyperparameters for that loss function. And that can be really valuable because the cost of over predicting a value might be significantly less than the cost to under predict a value. So you might want to try and prevent under prediction, and you can include that sort of information in the loss function so that the model that you end up with minimizes the impact in your specific case. So let's start with a really simple loss function. We're just going to take the sum of the errors. The sum of the errors is the difference between the predicted and the actual amounts. So what is the gap between the dot and the straight line value? So for our 1 plus 2x, our yellow line, we have 0 error on our first point. Yes, I can draw. So 0 error here, 0 error here, but we have 1 total error there, -1 error there, -1 here, -2, -2, and -3, or the opposite sign. So we can sum up all of those errors to be able to get a metric as to how it performed. And we can do that for each line. And as a result, we can see that our red line, our 2.5 plus x, ends up with an error of 0. That sounds like it's perfectly predicting our model, our data. The problem is, because we're just taking the sum of the errors, our errors actually cancel each other out. Because we've got a +1 and a -1. So it looks better than it actually is. It sounds like it's perfectly predicting, but it isn't because of our choice of loss function. So you won't normally see something like the sum of errors being used, but it's important to realize that your choice of loss function governs which solution is counted as optimal. Similarly, your loss function, because it looks at some value across your entire data set, a model can end up being selected based on the value in the loss function that might not actually be what you might consider optimal. In our sum of errors, both of these two lines, the red line and the blue line, have the same amount of error. But we'd probably all intuitively say that that red line is a better fit at predicting values than our blue line. So if our optimization process found that blue line first, based on our loss function, it might stop at that and go, I've solved it. I've got 0 error. Go me, I'm done for the day. So we also need to remember when we do machine learning that just because a model gets fit and answers the loss function in terms of optimization, it's not necessarily the best model that could be arrived at from things like a quantitative perspective or a business domain perspective. So you might need to then add some other constraints to ensure that you arrive at a solution that meets other requirements than purely optimizing this loss function. You might also see it represented not as called a loss function, but a cost function. There's lots of synonyms in data science. So we started out with a calculation of error between the difference between the predicted value and the actual value inside our loss function. The reason for that gap is actually many reasons. One is called bias, and we get bias because we're trying to simplify. We take a rule and we apply that rule to all the situations. But a single rule doesn't map to the real world. The real world is inherently complex. If you could build a rule that perfectly mimicked a process, you probably could have just used the rules that process was exemplifying. But with humans, they tend to be a bit fuzzier. So when we simplify, we get bias because we're purposely losing detail. But we can also get bias from getting really specific. So doing things like trying to predict somebody's height. You might oversimplify by taking their parents' height and averaging them and using that to predict. That might be an oversimplification, and the error would be as a result of bias. But you could take their parents' heights, their parents' nutrition throughout their existence, the individual's nutrition, their education, their work history, and end up with like 100 columns or features in your data set being used to try and predict the value. And that might get you to be overly specific so that when you go and start using that 100 column wide formula to predict new values, it might not work very well because it kind of overly learned from all the specific data that you trained the model on. You can also get measurement error. So this comes in particularly in bigger, longer running companies where metrics might have changed over time. So the definition as to what was counted, how the value was captured in terms of precision, the meaning, changes in regulations, all of these different things, as well as things like instrument error, can account for changes in values where we think it means something and it doesn't, but it actually meant something else. So we can get error there as well. And finally, there's always some irreducible error. People are crazy. There's this thing called quantum mechanics, and we just do different things. So we might be able to get a really good model, but there's almost always something that happens in real life that means we can't always fully predict what's going to happen. So there's always going to be error. I usually tell people when you're starting out, if you find yourself with no error in your model, you've probably done something wrong, and check and make sure that you haven't included something that is actually part of the label inside your model. So we get a lot of different error, and we get this in regression types of models, those lines, because we're simplifying. If we add lots of columns to make that line complicated, we might be too specific to our training data. And because we're using numeric values, if there was any difference or changes or calibration issues in our training data, we might not generalize well when that solution gets fixed. So the two terms that we usually think about here around error and how many features and things like that we include is overfitting and underfitting. So overfitting is a high variance situation where we have those 100 columns and it gets really specific. The problem is that when we get new data, it doesn't generalize very well. But if we underfit, if we only have a very, very simple model, like taking the average of everybody's values and saying we're going to predict the average in future, that has really high bias. It's too simple. So we need to find the trade-off point between bias and variance between underfitting and overfitting so that the solution minimizes error on the data we use to produce the model, but will continue to minimize error in new data that it has never seen before. So you get this trade-off. Okay. So we've talked about some of the key concepts that we'll be deepening in regression and how these concepts of fitting the model, the loss function, and error work inside regression. Does anybody have any questions at this point? Because it's important we make sure that any questions are answered now, because we're going to build on the concepts next.
There are no questions yet, but I encourage everybody to enter your questions in the Q&A if you have any questions going forward for Steph. Yeah, still don't see any, so.
Okie dokie. As Kathy said, please enter questions as we go along. Hopefully I've got the slides just right so that the question is answered on the very next slide, but do feel free to ask questions. So we talked about machine learning, and we said that we have supervised models where we have labels, things we're trying to predict, and features, which are things we're trying to predict that value by. We'll look more into that. We'll overview some of the key assumptions that regression makes, because if you fall foul of those assumptions, then as the classic phrase says, assumptions make an ass out of you and an ass out of me. We don't want models that we build to end up in the real world being harmful to others or just not being very good. So we need to make sure we're really verifying our assumptions. I'll then cover link functions so that when we look at data that isn't just a numeric value, we know how we can get a regression model to work with those. And then I'll cover the key loss function that most regression algorithms work with so that you can understand some of the assumptions and how this model, any trained model, ends up being arrived at. So a regression, you might also hear regression to the mean, takes a numeric combination of variables to predict another numeric outcome. So it's going to combine values, usually through a process of addition. So we're going to, in our y equals mx plus c, we're going to take some unit of x. We could add any other number of variables into that. And then we're going to have some intercept, which represents the error of kind of where our solution can't explain it just through the features. So it's the y equals mx plus c. As we add more columns, we get additional value, additional m's and additional x's effectively. Lines of best fit are its simplest, and it becomes quite difficult to visualize the relationship when you have multiple columns. Quite often, what you'll see is people showing the predicted versus actuals in different combinations of features or variables that are used to produce the model. So the features that go into a model for regression must be represented numerically. So we all have columns of data that might be useful things like countries, states. If you're dealing with something like demographic predictions, you might have ethnicity, religion, things like that. Or you might be trying to do something like trying to predict how much people will spend next year based on their reviews of products they've bought. So you'll not just have distinct values like countries, but you'll have full text. So if we want to use columns like that, we usually need to convert them in some way to a numeric representation. You also need to do what's called handling of missing values. So a regression model usually can't produce can't optimize when there's missing data. So if you include a column that's called sparse, so it's got a lot of nulls in it, a lot of missing values, then everywhere there was a null in that row would be removed from your training data, most commonly. So you need to decide how you're going to handle missing values. And I'm not going to go into detail here today, but how you handle those missing values can be done with what's called imputation, where we have a rule or even another machine learning model to predict what those missing values would be and fill them in. So you can get very complex situations for missing data. And the real world is messy. Things very rarely meet some of the statistical assumptions that are needed for regression models. So we can pre-process variables so that they actually start meeting those assumptions more closely, so we can end up with a better solution. All of these steps, handling missing values, pre-processing variables, what's called encoding, so turning the categorical and text values into a numeric representation, all of these are part of what's called feature engineering. A really key part of the process of building a model. So, regression assumptions. Now, this assumption, the sample represents the population, is an assumption that all of machine learning fundamentally makes. So it means that your training data, the data you're using to fit a model, is actually lifelike. So that usually means that we also have this belief and this assumption that the past and the future look quite similar, because we're almost always using data that has been produced in the past to be able to make predictions in the future. But the problem that you can get is your data might be too old and the future may no longer look like it. And we have that very much inside our post-pandemic times. We had all sorts of machine learning models to be able to predict how many units of stock of something would be sold, how many people would be flying, all of these different regression challenges, all firmly based on pre-COVID travel expectations and consumption patterns and things. But we drastically changed our behavior. So now, if we took a sample of data that included anything before kind of January, February 2020, our sample would no longer represent the population's behavior now. So that's your key assumption that you should always be thinking about. Does the data I'm training a model on actually reflect the data that I'm going to be making predictions for? All our features should be numeric. This next one can be a doozy. Features are independent and uncorrelated. So I mentioned earlier that our outcome variable is called dependent, and our input variables or features are independent. That means that the outcome is dependent on the things that kind of on the X side of our formula, but also it should mean that there's no relationship between between the columns being used on that side. In reality, this very rarely is true because, coming back to predicting height, your income and education level, which might be telling of like nutrition that you had as a child and stuff like that, which can impact your height, income and education level have a strong correlation. So we often need to do processes that can reduce the correlation between values inside our model and also explore the relationships before we do that modeling to make sure that our features are relatively uncorrelated. We also assume that the outcome can be predicted by our features. We know we're never going to get 100% fidelity on that prediction because people are weird, quantum mechanics. You never know every piece of information possible, but that the outcome is broadly dependent. Inside a regression, we also assume that the relationship between that combination of features and the outcome is consistent, so that the usually like the linear relationship, the straight line between height and things like income will behave the same, will have the same relationship, the same slope from a low income to a high income. That is one of the things that we tend to find varies the most inside businesses for the sort of things we model. So we need to we always need to check whether areas of our model fit better than others. And we usually look at our customer segments or other other groups to see how the solution varies across those segments. And the combination of variables should be normally distributed. A normal distribution is that bell curve that you might have seen and basically says that most values should be close to the mean, and some values, values will only very few will be very far away. That is kind of complicated. So here's a diagram for it. We have two features, in this case, Y and D, and they're normally distributed themselves. The pattern that we see when we combine those values, or if we're scatter plotting them, is kind of a smudge, which is denser in the middle and looks a little bit diagonally oriented because the low values and the very high values for each field are very unusually selected. So this multivariate normal is, again, another one of those assumptions that you need to check, that is valuable to check for and do feature engineering to help ensure. Let's talk about the link function, which is a new term. It's the relationship, it's the way that we translate the value from our linear combination of values on our X side to be able to predict our outcome variable. The reason we have link functions is because a lot of the things we want to predict are not a continuous numeric variable. So even something like height is a continuous variable in that, you can be 161 centimeters tall, you could be 161.1. So it's a continuous variable, but it would never make sense to predict a height of 0. Or there's like a theoretical upper bound on height. Things like counting cars or discrete numbers, so things that are in whole units, like how many people will fly on a given plane. That's a kind of a discrete number, and we need to change our linear regression to be able to cope with only outputting whole numbers. And similarly, one of the most commonly used regression methods is logistic regression. And with logistic regression, we're trying to predict usually a binomial or binary or discrete outcome. So this will be, will they go to college or won't they? Will this person pay their loan or not? What is the probability that this person will purchase this product? So a 0 and a 1 type of outcome, it can be only one or the other. Trying to predict that with a numeric value is actually really, it doesn't make sense to say somebody has a 0.5 or a 3 option of buying a car. So we do the same linear combination of variables, but the y that we're predicting is actually a transformation of our outcome that we're trying to predict. So instead of trying to represent the will they, won't they, we instead use a function described here to say that what is the odds or the log odds of them doing this thing. So we basically start describing the probability or odds of something happening, because then we get the numeric value. So any regression, the core algorithm of regression can, based on a linear model, using a link function, describe a large variety of different distributions that you're trying to predict. So you can predict binomial outcomes, true or false. You can predict whole numbers, and you can predict a variety of other types of numeric distributions. So the link function is the bit that varies based on what you're trying to predict. And then we have our loss function, the other key component for regression. Inside most regression linear models, we use this concept called ordinary least squares. It's ordinary because it's boring, we use it all the time, and it's least squares because we're trying to minimize the amount of the size of the squares that we can produce. What does that square mean? So the name for the gap between what's predicted and what actually happened is also known as the residual. Basically, what is the residual error after our prediction? Now, we saw earlier when we did the predicted versus actuals that when we when we took our over predictions and under predictions, they could cancel out. So what we often do, because we need errors we need the absolute size of the error, is we either do the absolute, we remove the sign, so all values are positive and they all add up, or we square the values. So we basically produce the little areas of them. And this means that the bigger the gap, so for instance, this gap here, because we square it, actually becomes really big. So we get a really large amount of error for what's called outliers, things that are really far away from our predicted value. So we square all of those. If there is no error, we end up with a zero error for that specific point. We take all of those squares and we sum up the area of them. So the sum of residual squares. And then we average that basically. We divide it by the number of observations, and that gets us a measure of error for this model. So you get a total value of the mean squared error. And if we square root it, we get just the line, the value on that one side of our square. So we use this figure to then be able to compare across multiple potential lines. So now we take our line that was in the middle, and each of our points has error, but they all have quite a small amount of error. So then when those add up, they end up with a fairly small amount of error. And we can compare that output from our ordinary least squares loss function with our prior model and say that our new line has a smaller amount of error than our old line. So this new line is better. And that's what ordinary least squares and the most common loss function it is fundamentally all about. It's taking the errors, squaring them, and comparing those values. Okay, so we're now going to talk about specifically linear regression, but do we have any questions before we move on?
No questions, Steph. So anyone have questions, be sure to enter them. And there's about 10 minutes left for the presentation.
Okay, so let's talk specifically about linear regressions. We've seen a linear regression used throughout this solution, throughout this presentation. So we're looking to find the optimal line that best describes the relationship between X and Y with a combination from X that we're building. So you should all be fairly used to this diagram now. Let's look at how we can be thinking about some of the bits that go into this that take it to that next level of complexity. So the first thing to know is that ordinary least squares makes the models very sensitive to outliers. Because it takes the square of the errors, a bigger number produces a bigger error number produces a much bigger amount of error that gets counted for optimizing. So when you're looking at your features, it's really sensible to be looking at outliers and deciding what you're going to do with them. So you might drop outlier rows, you might cap them, you might go back and check that the data quality is correct and high. So you need to check for those. You'll usually process your categorical variables, so your text. A common way to do that is one-hot encoding. You might also know that two variables impact each other. So the assumption that the features are independent and uncorrelated might not be true. So what you can do is you can instead, you can include them and their interaction. So you build a model that explains the impact of columns A and B and their relationship between each other, A, B, to be able to separate out the effect each feature or column has. And the other bit that you might do is bring all your different numeric values into a similar numeric range. We said that, like outliers and stuff can distort your calculations. So if you had something like income, where people might be from like 0 to a couple million a month, that very wide range with a 2 million value might really impact that fitting process. So instead, if you turn that into a description of like how many points of standard deviation each value is away from the average income, then you can put things on a similar scale and it won't be quite so sensitive to those outliers. So these are 4 practices that you need to be thinking about for linear regression and probably most regressions as well. And I've left in here how one-hot encoding happens. It basically gives you 1 and 0 flags for different labels, describing that interaction relationship, and another type of scaling process to put numeric values on a similar range. We've been looking at the y equals mx plus c. When we do those categorical variables with the 1s and 0s, they basically become Boolean flags. So you have a coefficient. So it might be like it adds an extra 3 if it's an apple. And if it's not an apple, it doesn't add anything. That's essentially adding to the intercept. The categorical variable won't change slope. The 2.5 before the x, that represents the correlation and the strength of the relationship between the value and the output or the label. And it's important to note that it represents, if you change x by a unit, so increment it by 1, the coefficient describes how much y should change. And that's important to remember because if you rescale the features, so you normalize them or you min-max them and you put them on similar ranges, you're not actually using x, its original values, in your model. You're using its rescaled version. The sign can indicate correlation. So positive numbers say that y increases as x decreases, as x increases. The different platforms, because we have lots of columns, not all of those columns might actually be useful and have a relationship with our outcome variable. So when you look at a solution, at a result where you've coded it, they actually do statistical tests that indicate whether the relationship of each feature in your model is actually useful and strong enough for it to be included. and we get a standard error that indicates basically what kind of range that coefficient could be. So all of that can sound quite overwhelming. So let's look at some data, at an example. So here's one I did in R earlier. I'm trying to predict how much distance cars can travel based on their speed. So distance is my Y and speed is my X. And then I get residuals. These describe the differences in my predicted versus actuals. So my worst over prediction was by 29 points, and my worst over prediction was by 43 points. But I have two key parts. My Y equals mx plus c. So my intercept is my c and speed is my x. The standard error describes the kind of like rough range, plus or minus, that we could be off by in our prediction. And the estimate is these, and sorry, the standard error is these. So our standard error on our 42.98 for our intercept is plus or minus 2. That's pretty good for our range where we could be from 0 to 150. That's fairly stable. And our 3.9 multiplier on our speed could be off by 0.4. So it could be as low in the slope on our line of best fit could actually be as low as 3.4 or could be as high as 4.3. We can, as well as the scale of the potential error in our slope and our intercept, we can check our p-value tests, which are these asterisks that state the strength of doing what's called a hypothesis test to basically see whether it's actually any good. So with 3 asterisks, it passes a really strong significance test to say that, yes, this actually is pretty good. So the intercept here is strong, as is our slope. They might not be perfect. They might be off by a little amount, but the relationship we're describing is broadly expected. And then once you interpret those different bits to see how the model is fit, what relationships it's describing, you should also be further evaluating whether the model is any good. A common one for linear regression is the R squared, or you'll see it as R2 because who has time to superscript things? This represents the improvement over just taking the average. So if it's less than 0, it's worse than just guessing the average. That's a really, really bad model. If it's the same, if it's 0, also not a very good model. It'll be good somewhere between 0 and 1. You're usually looking for a value at least over 0.6. And again, if you get an R squared of 1, that means you had no error in your model, which means you've done something wrong. And we can take our kind of loss function, like our root mean squared error, used in ordinary least squares, to predict values on our test data and see what the error is like on that test data. So if it's really high, then we don't want to use the model. So smaller is usually better. So here our R squared is 0.65, not great, but certainly better than just taking the average. We need to look at whether we get things wrong across basically, do our errors look like error for stuff we can't account for, or is there some pattern demonstrated that we need to account for? Basically, is it random or not? So looking at some of the errors for our existing slopes, our y equals 1 plus 2x got our early records correct, but got increasingly higher residuals as x grew. So there was a variance in how our model performed, which demonstrated that the relationship wasn't accurately captured. That's these ones. That concept is called heteroskedasticity. I try to never ever say that. And as we add more columns, as our model gets more complex and error starts creeping in from variance, we need to add more and more rows to be able to better account for a lot of variation in our data so that we don't get that high error due to learning too much about too few rows. So I ran a bit over, very sorry, gonna wrap up now.
Okay.
So today, continue attending. You're gonna learn a lot. I highly recommend you learn to code, whether it's R or Python, to help you do these things, because nobody wants to do a linear regression over 8 million records by hand. And there's some really useful follow-up resources on the link that you can learn from. So thank you all very much. Hopefully not too much brains bleeding out of ears, but you should now understand some of the key ways that regression algorithms work so that you can better produce new solutions in future.